That's a that's a good excuse.
But then
Yeah,
again, we'll have to do an extra class, Abhishek. I guess you're fine with that?
exactly. It's better to get over with. It's better to be done with with this class.
I
I,
mean, if Biden gets a second term, I'm completely fine with that.
yeah, I'm really happy that Biden won. I'm really actually I'm very happy because yeah, because Trump was one of the reasons I had to leave the country. He was not the reason, but he was one of the reasons that I had to leave because my EB2 visa was rejected, so I had to reapply, and then I got this job. I had to leave. So I'm really very happy. Okay. Okay. I spent a lot of time in the last 3 days watching the news and following the results. Yeah. Okay. Can we start? Is it okay or?
There are still around 64 people left to join, if I'm not wrong.
Okay. Okay. Let me share. Let me share the PPT. Where's the PPT? What's going on? There you go. All right. Are you guys able to see the PPT? See the notes?
Yes, sir.
Yeah. Okay. Okay. So can I start? It's 1:22, so I'll just start because I might have to leave early as well. We're already 15 minutes late. Okay. Okay. Sorry to cut to chase, but I had to do this. All right. So I was talking about intrinsic and extrinsic semiconductors last time, and I was talking about doping and how that changes the electron and hole densities. Okay. Now I'll continue on that, and we will derive some expressions for the charge density, electron and hole density in conduction and valence bands, and express them as a function of temperature and intrinsic charge densities. Okay, so you guys know that intrinsic is undoped and extrinsic is doped. So basically, you intentionally dope these systems. You add impurities to these semiconductors like silicon and germanium or gallium arsenide. You add impurities. If it's a fourth group element, let's say if it's a silicon, you add a third group element for creating holes, and you add a fifth group element to create electrons. Okay, when I say group, I mean that actually gives you the number of valence electrons in the atom. Okay, so let's say a fifth group element, like say phosphorus, has 5 electrons in a valence in its valence, the valence electrons. So it can offer one more electron to the semiconductor, a free electron, which is kind of weakly bound to the impurity. Okay, so that's what I said right there. Okay, and so what happens is when the phosphorus atom gives out an electron, that electron doesn't float away right away. So because that electron is kind of weakly bound to the phosphorus atom. So if you remove that electron, the phosphorus atom would become a positively charged ion. So that would attract the electron back. All right. So you will have a kind of a hydrogen atom-like scenario where you have a positive charge and the electron going around the positive charge. The free electron is not really free at all. It is kind of bound to the phosphorus. Okay, so you can use a hydrogen atom picture to calculate the radius and all that. We're not going to do that, but what I can tell you is the amount of energy that is needed to take that electron out of the phosphorus ion's influence is about 1,000 of the ionization energy of hydrogen atom. Okay, the ionization energy of hydrogen atom is about 13.6 electron volts. So you need to supply that much energy to get the electron out of the influence of the positive nucleus, right? So in this case, because the phosphorus atom is embedded in a material, already it is embedded in a material, the electrostatic attraction between the positive phosphorus nucleus and the electron is reduced substantially, right? So there's not going to be much electrostatic attraction between the positively charged impurity and the electron. So you can easily extract the electron, or rather release the electron from the influence of the phosphorus atom. So the energy for that is about the order of milli-electron volt. You've said here is about 25.8 milli-electron volt. It's not electron volt, it's milli-electron volt, so it's about 1,000 times smaller. Okay, whereas for the hydrogen atom, it's 13.6 electron volts. All right. The minus is because you have to supply that energy. Okay, the energy doesn't come out, but you have to supply that energy to the system. Okay, so when you look at the semiconductor with impurities at temperature T equals 0, okay, when there is no temperature, when temperature T equals 0, the electrons are going to be bound to the phosphorus atoms. All right, if it is if you're doping it with the boron, let's say, then the holes are going to be bound to the boron atom, right? Now, as you increase the temperature, there comes a point when the temperature, the energy from the temperature is going to be enough for the electron to be released from the influence of the phosphorus atom, right? Just like, or the holes rather, the holes and the electrons from phosphorus and boron, okay? So at a temperature, usually that temperature is about 100 Kelvin or somewhere around 100 Kelvin. So it's well below room temperature, right? At that temperature, the phosphorus impurity or the boron impurity or any other impurity in a semiconductor, those impurities get ionized, okay? Which means that the electrons or holes that are bound to those impurities would be released into the meat of the semiconductor. So those electrons are now free. The electrons are holes, whatever it is, they are free. They can freely roam around in the crystal, in the semiconductor crystal, right? So at that point, your intrinsic semiconductor, before that ionization, your semiconductor is intrinsic, right? It doesn't. The only free electrons are from the semiconductor itself, okay? And after 100 Kelvin, or somewhere around that temperature, you get extra electrons or extra holes, right? So that becomes extrinsic, okay? Your impurities become ionized, that becomes extrinsic, and the behavior of your semiconductor from then on is going to be extrinsic, right? And when you go to higher and higher temperatures, at much higher temperatures, actually the semiconductor becomes intrinsic again. Okay, we'll talk about that later. Okay. So I'm just listing out some of the ionization energies. These are available on Donald Neiman. If you have the book, these are already there. Okay, I just copied it just for completeness sake. You can take a look at it. It's about 45 milli-electron volt for phosphorus in silicon, 12 milli-electron volt for phosphorus in germanium and stuff like that, okay? The values are different because the effective mass, these values are dictated by the effective mass, okay? I'll argue that later down below, okay? This is for the gallium arsenide. Those energies are in electron volts. Okay? So these are the binding energies. Binding energies mean these are the energies, this much is the energy that you have to supply to get the electrons out from the phosphorus, right? So take the electron from phosphorus orbit into the conduction band, okay? So from the impurity band to the conduction band, that is the amount of energy that you need, Okay, so there is an impurity band created by the phosphorus impurity or arsenic impurity. So this is the amount of energy that you have to go from that impurity band to the conduction band. Same here for boron. Okay, let's say in boron you have holes. So this is the amount of energy that you need to get the hole from the impurity band created by boron to the valence band. Okay, so the holes always fall down when you increase the temperatures, because the electrons go up. Okay, when you increase the temperature, the electrons go up in energy level. Because the electrons go up in energy levels, the holes actually fall down. So when for the holes, the increasing energy goes below in the opposite direction as to that of electrons. Okay. Okay. So the ionization energies above are directly proportional to the effective masses. I'm not writing down the equation. You don't have to remember that equation, but the point is that the ionization energies are directly proportional to the effective masses. Okay, so higher the effective mass, higher the ionization energy. All right. All right. So we calculated the total electron density in intrinsic semiconductor as a product of two factors, if you remember. One of the factors is the density of states function. The other factor is the Fermi-Dirac distribution. Right? Remember, I also talked about this last time. The density of states gives you the number of possible states available within an energy range. And the Fermi-Dirac distribution function tells you what is the probability that these energy states are going to be occupied. So your total electron density at an energy E, or rather it's not precisely energy, it's E and E plus dE between those energy levels. This is the total number of electrons in the conduction band. This is the product of the density of states times the Fermi distribution function, right? We talked about it last time. Okay? This time we did that for intrinsic semiconductors. We're going to do that for extrinsic semiconductors this time. Okay. So VC is proportional to square root of E. Okay. This is the full form expression for GC. Okay. This we derived, if you remember, from in going from K space to E space. Okay, when you go from momentum space to energy space, this is what you get. The density of states is from that transformation, and your Fermi-Dirac distribution function goes as e power minus E over kBT. Okay, this is the full form expression. So there is a function that increases as a square root of energy. There is another function that decreases as exponential of energy. Okay, so you're multiplying these two functions. One is an increasing function, the other is decreasing function, and that creates a bump. Okay, a peak. Okay, so this is the can you guys see the whole thing now? The whole picture?
Yes, sir.
Okay. So this is it's a kind of a busy diagram. I'm sorry about that. If you want a clear picture, you can go to Donald Neyman. I could only do this much with a A4 sheet. So here is the picture. This the picture, actually you have to understand this picture clearly. The y-axis here is the independent axis. This is the energy. Okay, I'm basically inverting the. It's not me. Almost everyone who draws these curves have to do this. So this the y-axis is independent variable. X-axis is the dependent variable. Okay. Usually, what happens is when you draw a graph, you draw the dependent variable on y-axis and the independent variable on x-axis. We have just inverted it here. So the dependent variable is on y-axis and the dependent variable on x-axis. The x-axis, you're plotting two functions along the same x-axis. One is the Fermi-Dirac distribution function. The other is the density of states function. Okay, there are two density of states, one for the conduction band and the other for the valence band, right? And the Fermi-Dirac distribution function is the same function, right? It's for electrons, and for holes you just have to subtract 1 minus Fermi-Dirac distribution function. Okay, that gives you the distribution function for holes. So what you're doing is essentially you're multiplying this Fermi-Dirac distribution function and the density of states. So this function here and this function here, okay, those two functions. So when you do that, you get a curve like something like that. Okay. Over here, if the center, if the Fermi level, this center is right in the middle, this and this bumps would be the same. This and this peaks would be the same, right? But because this EF has moved towards the valence band, towards the conduction band, because we've added impurities, more electrons. So the middle has moved, which means the one this function has to go to 1 here. So that has moved closer to the edge of the valence band. So here, this 1 minus f of e is decreased quite a bit. Okay, so this product is smaller. Now you have less number of holes. Okay, if you integrate this area, this gives you the total number of holes. So the total number of holes is much smaller than the total number of electrons, because you've doped the material with electron donors. Okay, so this is an n-type material, as you can understand. Now there is an imbalance. Now we have created an imbalance. There are more electrons than holes, and the Fermi Dirac, the Fermi energy of the system has moved up. Okay, when I say Fermi energy, a physical understanding of Fermi energy is that the amount of energy that is needed to add or to remove an electron from the system. Okay, so when I say the Fermi energy has moved up, it just means that if you want to add one more electron to the system, you have to spend more energy, right? That's what it means. So the middle, the solid line in the middle is intrinsic Fermi energy, and the dotted line above is the extrinsic Fermi energy. The extrinsic Fermi energy is moved away from the intrinsic towards the conduction band. Okay? Basically, I'm just saying the same thing here. We can do the same kind of picture for p-type material. In the p-type material, you would have a smaller peak here for the electrons and a much bigger peak like this here in a valence band. Okay, this would be inverted, and the Fermi energy would have dropped down below the intrinsic Fermi energy towards the valence band. All right, so we have expressions. We have written down expressions earlier for the intrinsic total electrons in a material, total electron density in a semiconductor. Okay, and that is the equation. The equation is Ni. That's the total electron density of an intrinsic material, equals Nc. This is a constant which depends on temperature, which is called an effective density of state, times exponential EC minus EF intrinsic, EFI, okay, over kB2. So this is positive, which means this is a exponential minus some energy divided by kBT. Okay, as you increase the temperature, okay, this term decreases. A negative of decrease is increase, so this function increases, right? Same with PI. Okay, EFI minus EV is positive, and if you increase the temperature, this decreases, and exponential negative of decrease is an increase. Okay, so the intrinsic hole density and intrinsic electron density increases with temperature. NC and NV, these are the functional forms. All you have to do remember is that this is a function of temperature. It goes to T power 3 over 2. Okay. All right, so in deriving this, we made an assumption. The assumption was non-degeneracy. Okay, that's the assumption. Where what that means is that the Fermi energy of intrinsic material is far away from both EC and EV. Okay, that is the assumption. And once we made that assumption, we could write the Fermi Dirac distribution function as an exponentially decreasing function and do the integration. Okay. And you got this values from that integration over all energies to get the total electron density. So basically, we integrated Ni as a function of E over all energy E. Okay, so we did the same thing. Now we're doing the same thing for N0 and P0, basically the extrinsic electron density and the hole density. Okay, we're writing the same kind of equation, but this time it is EF, not EFI. The intrinsic Fermi energy was right in the middle of for the conduction band and the valence band. It was right in the middle, but EF can be anywhere. Okay, it can be close to the conduction band. It can be close to the valence band. It can be anywhere. So this EF is not the same as EFI. You have to remember that. And exactly the same as intrinsic equation. We're writing it here, except for the EF. Okay. Now we can write the N0 and P0 in terms of Ni and Pi. Okay. In terms of extrinsic hole density, in terms of intrinsic hole density, we're going to do that. So we can write the EC minus EF as EC minus EFI plus EF minus EFI. The EFI cancels, which is going to give you this value, this expression here. So it's the same thing. Okay, and you factorize that, you get this factor. This is nothing but the intrinsic electron density. So the extrinsic electron density N0 is intrinsic electron density Ni times an exponential factor. Okay. Now you can see that if the Fermi energy is closer to the conduction band, then this is positive. Okay. EF is higher than EFI, which means this is positive, which means N0 is going to be much higher than Ni. Okay. Whereas if the EF goes towards the valence band, this becomes negative and N0 decreases. So for if the EF is closer to the valence conduction band, which means you're in an N-type material, your N0, that's the electron density, actually increases. Okay. And the same thing for P0. Okay. P0 is Ni times exponential negative of that value. So if this increases, this decreases. Okay, you can see that this exponential some function, some factor here, exponential, the same factor with a negative sign. Okay, Ni and Pi are the same thing, so it's the same Ni. Okay, P0 equals Pi. You can write it Pi or Ni. It doesn't matter because in intrinsic material, Ni and Pi are the same thing. Okay. Okay, so you have two equations, N0 and P0. When you multiply those two, the exponential factor here, this is exponential some x, this is exponential minus x. So when you multiply them, they cancel each other out. So what you get is N0 P0 equals Ni squared. And this is an extremely important equation. Okay, this is a very important equation. You have to remember that. You will quite possibly get problems involving this equation in your exam. So you better remember this equation. Okay. So as I said, about derivation assumes that we are in the non-degeneracy. The non-degeneracy applies, which means that EC minus EF is greater than kBt. The energy between the valence band, the conduction band and the Fermi energy is larger than thermal energy. And the energy difference between the Fermi energy and the valence band top is again larger than Fermi energy. Okay. Only if that condition holds, all our derivation above holds. That's the non-degeneracy condition. If that doesn't hold, then we have to go back and do the integration without making the Fermi-Dirac distribution function into an exponential function. That integration becomes difficult. Okay. In that degeneracy condition, what happens is, when would that happen? That happens when the Fermi function, the EF, goes very close to the conduction band or very close to the valence band. That happens when you dope the system really heavily. Okay, when you really heavily dope the system, the Fermi energy goes far away from the intrinsic Fermi energy towards the conduction band or towards the valence band. And if it is really close to the conduction band or valence band, you cannot apply the non-degeneracy condition. This condition does not apply. Then EC minus EF is not going to be greater than the thermal energy. Okay, they're going to be very close. They're going to interact with each other, which means you cannot apply the non-degeneracy. Then you have to go for much complicated mathematics. Okay, we're not going to do that mathematics, but this is what happens. So EF here. Instead of below EC, it has crossed EC and it went above the EC. Okay, so in this case, even at temperature T equals 0, there are electrons in the conduction band. Okay, for a pure semiconductor, that does not happen. At T equals 0, there are no electrons because electron hole pairs have not been created. Okay, you create electron hole pairs by temperature. But in a degenerate semiconductor, you have electrons present above EC, even at T equals 0. Same for P-type materials. You have holes present because the Fermi energy has dropped below the top of the valence band, which means there are holes present even at temperature T equals 0. You don't need any temperature to excite electron hole pairs. Okay. All right. So basically, what that means is that because there are free electrons available and free holes available even at temperature T equals 0, it just means that these materials behave like metals. Okay. All right. I'll stop here because I have to go and prepare for the next exam. I have a Viva exam, so I'll have to prepare for that. I'll see you next week. Okay.
Thank you, sir.
Thank you,
No
sir.
problem.
Thank you, sir.
No problem. Yep.
Thank you, sir.
Thank you, sir.
Someone please download the material, download the video and save it somewhere. Okay.
Yes, sir. It's there in the drive now. Like all
Okay.
those old